All right. So, welcome to Monday, August 16th. Want to take this week to establish a lot of foundational ideas that are going to be really important throughout this entire year in this class. Starting with vectors and trigonometry, this is going to be critically important. Now, later on this week, hit a bunch of these ideas that maybe some of you guys need some review on. I want to make sure that we're all on the same page. We know things like algebra, basic graph shapes, scientific method, metric system, scientific notation, dimensional analysis, okay? All those kinds of things we'll look at next few days. Okay? Your guys' first quiz is going to be this Friday, and this is probably like the fastest turnaround we have. Just really short, just like a 1 week, just put all this stuff. But really, all I'm going to quiz you guys on is just vectors and trigonometry. So the stuff that we looked at today and how it's going to work out in terms of time also tomorrow. Okay. Now, do you guys remember this page that I gave you guys last week? This page right here? Right? I'm going to guess there's probably 2 or 3 of you that have lost it by now. So who needs one of these? Who needs one of these? Take mine. Let me know at some point. All right. So this page here is going to be your guys' first homework. This is what I'm going to pick up on Friday. I'll do a couple of these with you guys by the end of class today.
No, I don't need one. The sheet, I have like different numbers.
Oh, yeah, everybody's got different numbers.
Oh, okay.
Yeah, so I've created many versions. Oh.
I thought it was
Yeah. All right, so, yeah, so this is good practice to be able to work the way around a triangle. This I'm going to pick up Friday, unless you guys remember, I gave you guys some other options for homework. If you want to do one of those instead, show me your work, then that's all right. This is a skill you should be able to do to work your way around a triangle. So if you have a right triangle, you know a little bit of information about a right triangle. Can you figure out everything else? So we're going to focus on this today and a bit tomorrow. This other side, I wanted to do with you guys today, but probably tomorrow, I think. Just trying to get back used to these 45-minute classes now, coming off block from last year. All right, so you guys ready to go? All right. Oh, and normally I like to throw something like this on the overhead when you guys walk into class, so you guys get an idea of what's going on in this class, and then there's some kind of starter question. Now, here's my starter question. It's going to kick this off. It's going to take you guys through some notes. It's eventually going to lead to you guys being able to figure this out. I don't know. Maybe some of you guys can figure this out right now. Sorry, I got some pretty sharp students in here. Say I got a box that weighs 100 newtons. 100 newtons, think about that like 22 pounds. Now, that's weight is a kind of force. So is the weight pulling straight down? Yeah, the weight's pulling straight down. Oh, actually, I labeled it. See how I put a vector here? You guys remember vectors? Okay. I'm going to recap. That was you guys did. Okay. Now, is all 100 newtons, say, pushing perpendicular to the incline or pulling block along the incline? Probably some components to that, right? It probably has something to do with this 30-degree angle. Can you guys imagine? If this angle was smaller or larger, then maybe this block would have more or less tendency to slide down the incline. And these are my 2 questions. What component of the box's weight pushes the box perpendicular to the surface, and what component of the box's weight actually pulls it along the surface? Okay. Now, like I said, going to go into some notes that's eventually going to lead you guys be able to figure this out. But is anybody maybe able to figure this out before I get to that point? Who thinks they might know the answer to this question already? Yeah, Warner.
Is it 1/3 weight?
Ooh, good guess. Not quite though. Something else. Though. I bet what you're looking at is that 30 degrees is like a third of 90, something like that. Okay. Yeah, so different method we're gonna have to use to get there, but good guess though. Good job. Anybody else got an idea? All right, so let's hold on to this because we're gonna come back to that. I'll give you guys notes on. Actually, you know what I'm gonna do is give you guys some notes I gave you last week, but this is by design. I wanted to plant some ideas last week, and then now you'll have seen it and be like, okay, yeah, this is that much more familiar. Where's my ruler? No. Oh, here we go. Okay. Right, so let's start with a basic right triangle. Okay. Now, a right triangle, of course, is going to have a right angle in it. Not all triangles are right triangles. You know what? Let's slide this up a little bit more on the page. Look at the notes. Not all right triangles are, not all triangles are right triangles. Okay. But you can take any triangle and split it down into smaller triangles that are right triangles. So if you can work your way around a right triangle, like this one here, it has a right angle, okay, then you can make sense of pretty much any shape. You can split down something like this, right? Right, so I'm going to call, of course, alongside the hypotenuse. Okay. Of course, that's opposite of the right angle. Right. Then I've got two acute angles. So if I'm starting to make any sense of this triangle, I have to specify which angle I'm making measurements with respect to. Right? Is it the top one or is it the bottom one? So let me take this one bottom left. I'm going to label it theta. Right? Now, relative to this angle, you guys see that the two legs, only one of the legs is opposite of it and is not touching it at all. So I'm going to call it side opposite. And there's the other leg is touching the angle, so I'll call it adjacent. Yeah. There's no numbers up there. It's just specified angles and defined sides. Okay. Okay. Now there's definitions of ratios that are going to be important in this class. This is going to lead to SOHCAHTOA. This is a mnemonic device to remember what sine, cosine, and tangent stand for. Okay? These are, of course, keys on your calculator that there's like a fancy algorithm plugged into your calculator so you can calculate these ratios. Okay? But just to list the definitions out, sine of that specified angle theta is equal to the ratio of the opposite divided by hypotenuse, opposite leg divided by hypotenuse. Okay? That's what SOH means, right? So this is a sine, cosine, tangent, and then the next two letters are what the ratio is. Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. So we got cosine of the angle, like as a function, that's what it is, right? Like a function. It's the adjacent leg divided by hypotenuse. Okay? And the tangent of the angle is defined as the opposite leg divided by adjacent. Like that. Okay. Right, so that's very math textbooky. Okay, so that's all good, right? Okay. Now, in this class, how we actually apply this stuff, well, I'm going to rearrange this a bit. Okay. So normally how this works out is we usually care about right triangles because we care about vectors and vector components. Here's what I mean. Let's say that you started at this corner down here. Maybe you're on a giant campground. You guys imagine, so we're up in Yellowstone, and we're at this campground, and there's some campground that's like 5 kilometers away. It's way over here, like 5 kilometers away. Right? And maybe it's like a, I don't know, sneaky path or something. So how far to the east and how far north we're going to have to go, right, to get up to this campground that's like 5 kilometers away. Right? Well, maybe so many meters east and so many meters north that we have to go. Right? So maybe we can split it like this. Right? You guys are seeing these arrows that I'm drawing? Right? Or you could put it back together the opposite of the way that I just told you. Okay? So if you went so many kilometers to the east, and then you went so many kilometers north, then you would end up at the campsite that you care about. Okay? And in the way that I just told you guys, that version of it, see how I've added these two arrows together, tip to tail? See how the tail of this guy is kind of to the tip of the sky? Okay? So many meters over, so many meters up. Okay? And that gives me a resultant. You guys might remember that from last week too, right? This resultant. Okay? Yeah, so most of the time in this class, that's how it works out. So I might want to know, say I knew what the hypotenuse was and I knew what the angle was, could I solve for the two legs? That's usually how we apply that in this class. What I'm going to do is take these two, the sine and cosine definitions, and I'm going to rearrange them. Okay? I'm going to solve for what is the opposite leg and what is the adjacent leg, assuming that I know the hypotenuse on each one of those. Okay? Give you guys another example while I'm in the middle of so let's suppose there's some object in the middle of the floor and you push it up and to the right. Right? How much are you pushing it up and how much are you pushing it to the right? Well, that's also this question. What are the opposite and adjacent legs? Right? If you know like the force that you're pushing it with. Right? So you usually know like this number in this class. Could I say this one? That the opposite leg is equal to, now I'll do an algebra review with you guys later too, but hopefully you guys remember this. I can take this denominator, hypotenuse, and cross multiply it up. Is that okay? So I could say hypotenuse times sine of the angle. And I could do the same idea with the next line. So I could say the adjacent leg is equal to the hypotenuse times cosine of the angle, right? Okay. Now this right here, I'm gonna put in a box, because this is really important in this class. Okay. What's in that box there? Know that by heart, because you're gonna be using that a bunch this year. You're gonna use that projectile motion, two-dimension, time motion, forces. You'll see it over and over. Okay. All right. Some other things you can know about this. You know what? Here, I want to take this last one. I'm going to rearrange this too, but maybe in a little bit different way. Okay. So what if, let's go back to the example I was saying we were at a campsite. So we're in Yellowstone. We see this hypotenuse is like 5 kilometers away. Right? You guys know one special kind of triangle is called a 3-4-5 right triangle, right? Yeah, now, obviously not all triangles this, but it shows up here and there. Maybe this happens to be that, just for sake of argument. What if to get from here to here, from point A to point B, we go 4 kilometers to the east, so I'll call this 4 kilometers, and then 3 kilometers north. So just to give you guys one example, right? So 4 kilometers east, 3 kilometers north, right? So that you ended up 5 kilometers distance from where you started. Right? But the question now is, can you figure out what that angle is? Because notice I did not actually tell you what that angle is, right? Which we kind of need to do everything in the box, right? Does anybody know how to extract an angle from a problem like that if you know a bunch of side information? Thea? Inverse, yeah, like inverse trigs. Yeah, so do you guys know inverse trigs? Right? I'm gonna rearrange this last one. You can do this with sine cosine too, but I'm gonna do tangent. So notice that tangent of some angle is defined as some ratio, right? And your calculator has memorized all the possibilities, right? What if I would really like to extract this angle theta. Couldn't I just like undo the tangent on both sides? That's called inverse tan. It's also called arctan. Right? You guys ever heard of arctan? Right, so the notation looks like this. It's like 10 to the minus 1. It's not really a minus 1 power, or I don't think it is. I think it's just notation. But of the 2 legs, opposite over adjacent, right, that will tell me what that angle is. Okay. Let's try it out for that example that I told you with like walking around in Yellowstone. So just eyeballing that triangle. It looks kind of the 3-4-5 triangle, looks pretty close to. Does that angle look kind of close to 30 degrees, maybe about 30? Right? But probably not exactly, but maybe kind of close. Right? So I'm just saying that because it's good to check your work too. Say, does this make sense as you're going along? You're not getting crazy numbers. Okay. Let's try this. So let's do inverse tan. Oh, how do you access the inverse? Right? Well, do you see sine, cosine, and tangent on this calculator? If you have your own calculator and you want to use that, then that's okay. Just figure out how to do it. Okay. See above that in white letters? I see the inverse trig functions. You guys see those? And you access those by hitting the second key. So hit second tangent in this case. And oh, look at that. It's inverse tangent. Okay. Who's got questions so far? You guys know how to get inverse tangent? So second tangent. Okay. And then see opposite over adjacent. So if I do 3 divided by 4, and that's what I'm taking the inverse tan of, that should tell me what this angle is, right? Okay. And already just eyeballing it looks kind of close to 30 degrees. Let's see. Oh, it's about 37 degrees. You guys see 37 degrees? Okay. That's pretty close. I can believe that. Looks believable, doesn't it? Okay. You know that. Okay. What do the 2 acute angles in a right triangle always have to add up to, as long as the triangle is flat? 90 degrees. They should add up to 90, right? Okay. Because all 3 angles of a triangle should add up to 180. I mean, this is all math theory. We're going to look at the science after this tomorrow and see how true this really is. It is, but on a flat triangle. So take 180 degrees, subtract out the 90 from the right, you should end up with 90 degrees. So if this is 37 degrees, then what does this angle up here have to be? Should be 53, right? Because if I do 90, take away 37, I should get 53. Right? Or maybe now I have multiple methods to start solving these, right? What if I did inverse tan, but I just swapped the definitions of what's opposite and what's adjacent? So what if I take this out as my reference angle? Can I get it by saying inverse tan of 4 over 3? Can I do that? It should tell me 53 degrees. Let's see if it does. Inverse tan of 4 over 3 is, it's 53 degrees, right? Guys see that? Yeah, if you know how to work your way around a triangle, you know a few ways you can go back and check your math by doing other methods too. Okay. Who's got questions so far? Okay, so, a couple of details about a triangle. Do you guys know, I know everybody knows this. If you, no, okay, this only works for a right triangle. If you square the two legs, add them together, you get the square of the hypotenuse. Okay. How this was originally, well, give you guys one perspective on this. Okay. If you take, well, run out of paper, but if you could turn this leg into a square, like physically square the side, goes off the paper. Okay. You could square this side. Okay. Got a giant square right here. Okay. And then I've got this hypotenuse. I'm going to square this too. It's going to go off the paper. You could imagine a giant square that goes off the paper. Okay. This square plus this square adds up to this giant square here. Okay. 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 And you guys also know, I'm sure, how to take the area of a triangle, and that's just what? 1/2 base height. Okay. Going to use that a bunch in this class. Like a graph analysis. Yeah, you guys can use this all over the place in AP Physics. Okay. Make sure now everybody knows. If you forgot that, of course, area of a triangle. All right. All right, good so far? Okay. Okay, so we know how to split a triangle into, or sorry, how to split a vector into components. Okay. I do want to give you guys some examples of vectors. Let's throw some definition stuff. Okay. I won't write out a whole lot of definitions class because I did give you guys, okay. One of the pages I gave you was this, and it tells a bunch of definition type stuff. So, but you want to write down a scalar and a vector. Okay. So when I'm talking about these things, we'll for sure know what I'm talking about. So scalar is a quantity that has a magnitude. That means there's some number you can attach to it, okay? But not a direction. So, but no direction. Okay. And for example, okay, throw one at you guys. You guys tell me whether this has a direction or not. Okay, mass. You guys see this 1 kilogram weight right here? Right, one kilogram. Okay. If I take this up into space, does it still have a 1 kilogram of mass? Yeah, mass is like the measure of how much matter. Also in this class, it's like a measure of how much inertia. So if I push against it, there's some resistance to push. Right? If you were in the International Space Station, would you rather have a tennis ball thrown at you or this? Probably a tennis ball, because this is going to be a lot harder to slow down, even in space, right? So mass definitely has a magnitude, like 1 kilogram, right? But no direction, right? What do you think weight is? Do you think weight has a direction? Yeah, because Earth's gravity is pulling straight down, right? So weight is a vector. It's not a scalar. It's also a completely different unit. Like mass can be kilograms, weight something else. How about volume? Does volume have a direction? No, not really. Maybe you have a direction of flow. Same idea for energy. You can quantify it. Right? Like volume could be like so many cubic meters, so many gallons. Energy could be like so many joules, so many kilowatt hours, so many calories. But have a direction of flow, but not a direction itself. There's some technical ones. Distance and speed. If you use those terms like specifically true, then they're just talking about magnitudes. Okay. Let's talk about vectors. Okay. So a vector, well, singular vector, is any quantity that has a magnitude and also a direction. So I'll say both a magnitude. Magnitude means you attach a number to it, right? But also a direction. Sometimes that direction is implied, like forward or something, but it'll end up being important because when we start to add these vectors together, we'll have to use like tip to tail method. Well, graphically is one way to do it. Okay. to figure out something's going forward. See, is that in the north direction? And if there's a like a crosswind blowing east, and how does that interact with it? Okay. So, for example, you can put displacement. Remember that Yellowstone example I was just telling you guys? If you're at one campground and you want to go to another campground that's 5 kilometers away, now 5 kilometers by itself could be a distance, just about 5 kilometers, great. But if there's a specific campsite you're looking for, then it better be to the northeast or something. Maybe it's 5 kilometers at 37 degrees north of east, something like that. 53 degrees east of north. Okay. Velocity. Now, velocity, probably, well, isn't that like speed, like how fast? Yes, but here, direction specifically matters. There's some cases where how fast doesn't matter, when you like centripetal force kind of thing, but a lot of times it does. Okay. Acceleration, we'll talk about more next week. Force, for example, weight. There's a bunch of other ones, but those are some pretty good examples. I think you gave you guys a pretty good list of vectors on this page down here where it says trigonometry, and give you guys some examples of vectors. You guys good so far? All right, so let's get a step closer to the starter question that I threw at you guys, which looked like this right here. Okay. We got to this 100 Newton block sitting on a box sitting on this incline, right? So it's pulling straight down. There's a gravity force on it. Earth is pulling straight down 100 newtons. That's why I drew this as like an arrow. That's actually a vector, right? That's a weight vector. Okay. Remember my question was, well, how much is actually pushing the block right into the incline? How much is pulling it along the incline, like making it want to like slide down, right? And I want to approach this by thinking about that angle of incline. And what if we were to change that? Now, this is a really good tool to have in your toolkit in this class to be able to adjust variables. So we got a dashed line going here. Okay. You're going to draw 4 different scenarios of what this could possibly be if we're adjusting the angle of incline. Okay. So in the example that I threw up there, there was a 30-degree incline. So maybe I'll sketch that out. Plus 30 degrees. Right. Could sit a box right there on a 30-degree incline. Okay. But what if I adjusted that, made it even steeper? What to, like 60 degrees? Or what if I took it to another extreme, made this a wall, and I just put that block against the wall and just let it go, like a 90-degree angle. And then the other extreme could be, it could be sitting at just on a flat surface, like at a 0-degree angle. Got 0 degrees, 30, 60, 90. Right? And you guys imagine that incline ramping up. Right? If you want something a little bit more tangible, if you guys have a surface like a textbook or a binder, right, you probably put an object in there on a calculator and then start lifting the binder, opening the book, right? Probably get all the situations right there. Right? Or you can imagine this. Now, maybe this is an identical block for every one of these. I'm going to draw what's called a free body diagram. This idea will come back later. But for now, I'm just going to put a dot at the center of gravity of that box, straight down 100 newtons for each one of these. We should use blue for, why not? Switch colors. Make these all the same. Okay, so 100 newtons. These are all 100 newtons, pulling straight down. Okay. So identical block, identical weight, but differing surfaces. Okay. Now, here's how I want you guys to imagine this. Right, is we're adjusting the angle of incline. Okay. On the one on the far left, wouldn't it be true that all the block's weight is pushing into the surface, and 0% of the block's weight is making it slide horizontally to the surface? I mean, it's not going to start sliding horizontally, right? Right, so that's one boundary condition. If you go to the other extreme possibility, the one on the far right here, okay, isn't 100% its weight, just making it slide along the surface. And probably none of it's actually even pushing into the wall at that point, right? The wall doesn't even feel the push from the block, right? Okay. Right. And in the middle, it's probably transitioning from one to the other. So how's that transition process happening? Okay. Okay. You guys get that premise? Now here's what we'll do. I'm gonna take these middle two, since it's kind of small. I'm gonna blow these up bigger. If you can fit this on your notes, then I guess that's all right, but make sure my notes are really clear here. All right, so we're looking at 30 degrees versus 60 degrees, probably pretty close, 30 degrees, 60 degrees, block, block, center of gravity, blue ink, 100 newtons, 100 newtons, 100 newtons, 100 newtons, something like that. Okay. Now, remember how that question was actually phrased? We go back to the original question. Oh, and this picture on the left looks exactly like this original setup, doesn't it? It's the same thing. Is that right? Okay. And it says what component is pushing the block perpendicular to the surface, and then later on pulling the block parallel to the surface, right? Okay. We figured it out for the extreme ones, like for this one, the far left and far right. Okay. It's kind of 100% versus 0% kind of thing, right? What about this angle of incline? Well, what we really need is maybe an axis system that's oriented to the surface, because that's the question, is perpendicular to the surface, parallel to the surface, right? Right. Maybe more intuitively, there's an axis system that's aligned to gravity, also this weight vector, but I'm going to split this up. Bring in purple ink. So I'm going to introduce a new Cartesian system that runs parallel to each surface, but then also perpendicular to each surface. Perpendicular, perpendicular. Okay. So those purple dashed lines are parallel, perpendicular to the surface. And then what I want to do is take that original force vector, which is 100 newtons for each of them, okay? And I want to split it into components along the frame of reference of the Cartesian grid that I just created. So we're about to make right triangles, right? About to make right triangles. Bring in I got a green pen. Green pen. Okay. Right, so the number I have already, 100 newtons, is going to effectively be the hypotenuse of a right triangle. You guys hear that? Okay. Remember I told you, just make for sure, you guys remember this, that the way we apply trig in this class almost all the time, and we're about to do it right now, is you know the hypotenuse, and you know the angle, and you want to figure out the two legs, this box right here, right? Okay. That's what we're about to do. But it's going to be rotated, right? So this 100 newtons on this box on the left is mostly pushing the block into the incline. Wow, Mr. Griffin. Sure, where do you need me? 4, 2, 3, 4. Sounds great. Yeah. All right, I got it. Yeah, thank you. All right, so the shallow incline means that most of the way is pushing into the incline, and there's a little component that's dragging it along. I mean, if this was, for sure, if this was like an air hockey table, this would slide down, maybe not very fast, but kind of like that. Right? So notice those two dash vectors that I put, those are actually components, aren't they? Components of the weight, right? Is that? Right. And this is definitely a right angle right here. The two components are always going to be the right angles to each other, right? Okay. Pause right here, make for sure that you guys have got this. Notice this one that's down to the left. See how it's parallel to the surface? Parallel, right? In fact, if you want to, some textbooks actually put it up at the block, which is maybe more correct actually, but I like making a right triangle myself. So either way is fine. Right? But it is really important that it's parallel. Notice it's not parallel to the ground, it's parallel to the surface. Right? That's gonna be one thing that I'm gonna quiz you guys on. So make sure that you guys can all draw a parallel line parallel to the surface. Right? Okay. Let me do the same thing for this block on the right. Okay. So now this one's on a really steep incline. So a little bit of its weight's pushing into the incline, but probably not a whole lot. And mostly pulling along.
Pardon this interruption. At this time, please release the 10th grade bus riding collegiate student. Again, at this time, please release the 10th grade bus riding collegiate student. Thank you.
You guys good so far? Everybody? Okay. And now, what I'm trying to think is, okay, so I could get those components. I could get these two legs of the right, each right triangle, opposite and adjacent, right? Because I have hypotenuse, but if only I knew something about theta, if only I knew the angle, right? Isn't that true? Okay. So take a good look there. You might be able to figure this out, right? Maybe this top picture could help too. Produce side by side here. Okay. What angle do you guys think this is right here? Make a good guess. Versus here. How about that one? Does that look kind of like that? Does that look? Yeah, this one's going to be 60. This one's going to be 30. Yeah, good call. Yeah. Right? Guys, yeah? So now I'm not going to prove the geometry. If you're super curious about this, you want to take this home and really analyze the heck out of it and do all the geometry, you could. But yeah, those angles will always be the same. So that's 30, 30, 60, 60, and then you could do like 73, 73. Okay, guys got that? Okay. So now we do have a triangle, a right triangle where we can make sense of. Look at this right triangle right here. Look at this right triangle right here. Okay. And they each have a hypotenuse of 100 newtons. Okay. So let's say this component right here, this would be equal to, okay, I'm going to take my 100 newtons, that's the hypotenuse, 100 newtons, and I'm going to multiply by sine or cosine of 30 degrees. Sine, yeah, because it's opposite, right? Data got that? Okay. Yeah, times sine of 30 degrees. Okay. Okay. Let's see what that is. 100 sine 30. Now, if you have your own calculator, make sure your calculator is in degrees and not radians, because there's different ways to measure angles. Right? So if we're doing degrees. Okay. It's exactly 50 newtons. On the dot. Hey, you know what? I bet 30 degrees is a really special angle. What do you think that sine of 30 degrees is going to be every single time? Yeah, I hear a bunch of guys saying 1/2, right? Probably a good one to know. Okay. And hey, what about how much the block is actually pushing into the incline? How much do you think this is going to be? I think it's going to be 100 newtons times cosine of 30 degrees. And this calculator, all I have to do is scroll up, scroll over, flip in the cosine, and 86.6 newtons. Do you think that ratio you're probably going to see a lot this year too? 86.6%? Yeah, it's going to come up quite a bit. You'll see that again. Okay. How about this triangle? Hey, you know what? Taking a look at these two triangles. Guys, if this is 30 degrees up here, this little skinny angle, what's this bigger acute angle down here? 60, so that these two add up to 90, so they all add up to 180. Are these two triangles similar triangles? They sure are, aren't they? So I bet you guys can figure out what this short leg is right here without the calculator. What's this got to be? It's got to be 50 newtons, doesn't it? Right? Let's test it out though. 100 newtons times cosine of 60 degrees. Right, let's try it out. What's 100 cosine of 60? Oh, it's 50. Look at that. 50 newtons. You guys are on. You got that. And then for completion, flip in a sine. So 100 sine of 60 to get opposite of 60 degree angle. Oh, it's 86.6. 100 newtons times sine of 60 degrees. 86.6 newtons. Right there. Okay. That's it. Right. And then how about, you guys good so far? Who's got a question? question. Okay. Okay. Now, those two pictures, of course, are the middle two examples right here. Okay. What if I did this one? Okay. What is 100 newtons times cosine of 0 degrees? Cosine of 0. Ooh, cosine of 0 is 1, so full 100 newtons. So here, 100% of the weight is being pushed into the incline. And then what is sine of 0? 0, which means that 0 newtons are actually pulling the block along the surface. Okay, so yeah, you can plug in the extreme conditions, it still works. Okay. That's good. Okay, so the answer to this question then, well, you guys have got it right in front of you. Okay. Put these side by side, the question and then the solution. So what component of the block is pushing perpendicular to the surface? The answer to that is what? Yep, 86.6 newtons, or 87 newtons. And how many 6 inches you go? Okay. And how much is pulling parallel to the surface? 50 newtons. That's what's trying to pull it down the incline, right? Do those two add up to the original 100 newtons? Ooh, they do not, do they? Huh. That's interesting, but that's how it works. Yeah. All right, so we were on about 9 minutes. All right, we're doing all right. Sure. Okay, so one of the pages that I gave you guys last week was this one right here. It's this one. Okay, so my original intention was, I wanted to do this whole side of the day, but we're gonna have to say this another day to get used to this 45-minute schedule. Okay, so tomorrow, I think I'll have you guys break out the protractors. We're gonna measure some of these triangles. We're gonna see how do the observations and measurements actually line up with the math. Okay. This side here is going to be your guys' homework due Friday, unless of course you want to opt for one of these other options. But your guys' quiz is going to be very similar to this too. In fact, I'd be surprised if some of you guys could whip this out in like 10 minutes. So I'll do some of these with you guys though. Okay. We'll definitely do number 1. You guys look real close. Number 1, number 5. Scale number 1, number 5. I give you the same numbers. I give you the alpha angle on both. And I give you z, like the hypotenuse of the triangle. Okay. Definitely. I mean, if there's one that you just know like the back of your hand, then that's a good category to know. Number 1, number 5. Okay. Because that's usually what you have in this class. Normally, you know the original vector. Okay. You guys see this right triangle here? It's actually a vector that's split into components, like x and y components. Okay. That's normally what you want, is you know the hypotenuse, you know angle of incline, and then you want to figure out everything else. Okay. But you might have different information about either triangle or vectors, and you have to, so depending on your starting information, can you work your way around the triangle? Right. So I give you 2 pieces of, just glancing at each problem, you see that I give you 2 pieces of information about the triangle. Really, you have 3 because you also know there's a right angle on every single one of these. Okay, so, okay. And then can you figure out the other 3 things about the triangle? Right? And there's multiple methods to be able to get there. Okay, so let's do number 1. Okay. See, I gave you alpha, and all your guys' numbers are different. So mine says 30 degrees for alpha. So what does beta have to be? It has to be 60 degrees. Okay? Because alpha and beta have to add up to 90 degrees, because then when you add in the other 90 from the right triangle, it's 180. Okay? I gave you the hypotenuse. So how are you going to get the side x? What are you going to do? What's one way to do it? Can I do, 90 meters times sine of 30 degrees. Here, sketch this out. Okay. So this is 30 degrees. This is 90 meters. Maybe going 90 meters kind of northeast-ish, but that's a 30-degree angle. Okay. So this would have to be 90 meters times cosine of 30 degrees. This would be 90 meters times sine of 30 degrees. A little multiplication right there. Okay. So what is 90 cosine 30 degrees? That's the 77.9 meters. That looks believable. I mean, that's the longer of the two legs, 30-degree angle, kind of shallow. So I can believe, 77 meters versus 90 meters. That looks about right. And then if I flip in a cosine where the sine used, sine where the cosine used to be, gives me this guy is 45 exactly meters. Okay. Which maybe you guys could have done without the calculator because you guys know that sine of 30 degrees is exactly a half. Okay. You guys remember that from earlier? Okay. All right, so great. So I got these numbers. This is like 77.9 meters. This is exactly 45 meters. If I have three sig figs to work with. Okay. That's good fun. Okay. Now, there's other ways you also could have gotten these. I could have done 90 meters times, let's see, no, this is 60 degrees up here. Cosine of 60 also gives me 45 meters. That's a different way to get to it. Could have done Pythagorean theorem, right? Like Pythagorean theorem, if you know two of the, of the three sides of the triangle, if you know two of them, you can figure out the third, right? Maybe you know C and A and you want to solve for B. Can you guys do some algebra, subtract, square root, all that? Okay. Or we can check our work after the fact. So maybe you're looking at these numbers saying, let me try a different method to see if this all checks out makes sense. We do a squared plus b squared and see what I get. 77.9 squared plus 45 squared. And then if I take the square root of that, I should get 90. Is that okay? A squared plus b squared, and then take the square root, I should get hypotenuse. Okay, let's see. Square root. Let me show you guys a fancy way to take a square root. You guys want to learn a fancy way? Some of you guys might know this. Take this number to the power of, it's a power of what is the same thing as a square root? 1/2. Yeah. Okay, so you guys know that. So 1/2 power, or you just do power 0.5. It is 89.9 something. Well, some of these numbers were rounded going in, but yeah, basically 90. You guys see 90 meters? Same thing. Okay. Here we go. How about, I also want to do with you guys number 7. Let's do number 7. Okay. Number 7, I give you 2 of the sides and nothing else. Oh, it's the right triangle. You know that much anyway. Okay. Ooh. Well, let's start with getting Z. How could you get Z? Using the, Pythagorean theorem. Yeah. Okay. You know what? Look at the numbers on my page. How many guys see that this is how many guys can do this one in your head? It's, you might have different numbers than I do.
Oh, sorry, I do.
Yeah. Who said 10? Who said 10? Oh, all right. Yeah. Theo said 10? Right. Yeah. Because this is actually you guys see it's a special triangle? This is a what kind of triangle? Oh, what? This is a 3, 4, 5, isn't it? Right? Because it's just scaled up by a factor of 2. Right? It's proportionally the same. You can do Pythagorean theorem, get it that way. How are we gonna get those angles? How are you gonna do it? Yeah. Great. Yeah, you guys are saying some kind of inverse trig, right? Maybe I'll pick inverse tan. That's the one I usually go to. That's usually my go-to. Right, so hit second, the one of the trig functions, I hit second tan to get inverse tan. Now, if I do inverse tan, I have to play off the 2 legs specifically, right? So that would be like, see, 8 and 6, and I have to get them in the right order. So if y is 6 and x is 8, maybe I should do 6 over 8, right? Of course, that reduces to 3 over 4 anyway, right? 3, 4, 5 right triangle. And that is, hey, did this number show up earlier today? 37 degrees? Yeah, because anytime it's a 3, 4, 5 right triangle, it's got a 37-degree angle, 37 degrees. Okay? And if I swap the definition of opposite and adjacent, so 8 over 6, take the inverse tan, you get 53 degrees. Okay? And if you guys like inverse sine and inverse cosine, you can also use those. You just have to bring in the hypotenuse. So for example, you could do inverse cosine of 8 over 10. That should also give you 37 degrees. Let's see if it does. Yep, sure does. Or in inverse sine of 6 over 10. It's also 37 degrees. Okay, guys good there? Just got any questions? Anything so far today? Okay. So like I said, this is really foundational. Tomorrow, I want to have you guys break out the protractor, so I'll go over some of these with you guys. And we'll do a recap of some other things that's really foundational to this class. But all this trig stuff, is so important. This is really what I'm gonna be quizzing you guys on this Friday. Okay. So understand how to do these. So pick up Friday unless you want to do one of those other homework options. Okay. Also, you guys remember this whole page right here where I showed you guys how to place a block on an inclined surface and split that into components? Okay. Can you guys draw lines that are parallel and perpendicular to the surface? Remember parallel right here? These two are parallel, right? Okay. I make such a big deal about this because this is something that I see students struggle with year after year. Right? You guys see how these two pins are parallel? And this pin is, right? You guys parallel, right? If you drew it like this, that would not be parallel to the surface, right? Okay. These two are parallel. Okay? You guys can do that by Friday? Okay? So we'll do a little bit more practice tomorrow. Okay? We have 10 seconds class left, so I'm going to stop this recording and that's a wrap.